Everyone. My name is Ruslan, and I would like to share today the results that we described in the paper Self-Supervised Depth Correction of Lidar Measurements from Map Consistency Loss. Depth perception is considered an inevitable source of information in the context of 3D mapping and various robotics applications. However, point cloud maps acquired using consumer-level lidars suffer from bias related to local surface properties, such as beam-to-surface incidence angle. For example, if a robot equipped with a lidar is moving inside a corridor environment, the measurements of the floor typically have a higher incidence angle than the beams hitting the ceiling. The resulting measurement bias then negatively influences both the localization and mapping accuracy. Let's take a closer look at the bias origin. Consider an oriented surface which is measured by the LiDAR sensor. Here, the vector n describes the local surface normal, and the angle theta is the incidence angle between the LiDAR ray and the normal direction. For the real lasers, the light beam width is not constant along its propagation axis. That is why the intensity distribution is not uniform along a beam direction. When the LiDAR beam hits an oriented surface, a great amount of energy returns sooner to the sensor than if the surface was not oriented. To estimate the bias, we propose the following setup. The rigid calibration board is being tracked by the high-precision theodolite sensor, and at the same time scanned by the LiDAR sensor. The board could be rotated along its vertical axis, and we measure the average point-to-plane distance between the LiDAR points and the calibration board for different incidence angles. In this figure, you can see the dependence of the point-to-plane distance on the incidence angle as we rotate the board. For the large distance, 8.6 meters from the LiDAR to the board, we observe up to 10 centimeters inconsistency in terms of point-to-plane error for large incidence angles. That's the LiDAR measurement bias we aim to correct. To eliminate the bias, we introduce the function designed to correct the depth d measured by the LiDAR rays. We model the bias as the polynomial of the LiDAR beam incidence angle. It is additionally being scaled by depth to account for the non-uniform energy distribution along the ray. We propose the following self-supervised approach to learn the depth correction model parameters W. The depth correction model is applied to individual LiDAR scans. Provided the localization, the corrected point clouds are then transformed into a global reference frame. Given the global point cloud, a consistency loss is computed for the constructed map. Next, its gradient is backpropagated in the computation graph to update the model's learnable parameters. Additionally, if the localization source is not accurate enough, it is possible to optimize LiDAR sensor poses by learning the pose correction terms, delta t. Let's discuss further the map consistency loss design. The core assumption is that the scanned flat areas should remain flat in the global cloud. We would like to design the map consistency loss to penalize planar area misalignment in the point cloud map. Formally, eigenvalues of a point set covariant matrix describe point distance variance along the directions defined by eigenvectors. A planar area has a property that one of the eigenvalues is much smaller than the other two. The corresponding eigenvector is the estimated normal direction for the flat region. Therefore, to minimize the plane's misalignment in the global cloud, one should decrease the variance along the normal direction, or to minimize the minimum eigenvalue of the planar regions. We collect the following data sequence to train and evaluate the depth correction models. In the setup which we described previously, it contains point clouds captured in an office indoor environment with precise localization and ground truth mapping information. The point clouds and their poses are recorded with the clear path Husky robot equipped with the Oyster Lidar. The stop-and-go data capturing strategy allows recording LiDAR scans not suffering from an error caused by sensor movement. Is it then possible to improve the localization accuracy of the sensor once we have more accurate LiDAR measurements? To address the question, we benchmark the SLAM method introduced in 14 with the ground truth localization information. In the first part of the experiment, the SLAM pipeline was running using the raw sensor measurements. Then we execute the same procedure with the difference. Depth correction is applied to LiDAR scans before the ICP point cloud alignment. It can be seen from the table that removing the bias from LiDAR scans improves localization accuracy by around 9% in translation and 7% in orientation. To sum up, in this paper, novel point cloud map consistency losses as well as depth correction models were presented. To tackle the lack of ground truth depth data, the models were trained using LiDAR scans taken at multiple viewpoints of the same scene in a self-supervised manner. Once the models were trained, it was shown that with their help, the correction of LiDAR scans allows the construction of a high-quality point cloud map and reduces the localization drift. We release the code and dataset with accurate ground truth reposes and mapping information. Thank you for your attention.